Hello grade 11s and welcome to this video in which we're going to be taking a look at an example involving the electric field. Before we start, I'd like to remind you that we have three formulae now that we're familiar with. Firstly, we have Coulomb's law that allows us to calculate the electrostatic force, but only the magnitude of the electrostatic force. If you would like to know the direction, you need to ask yourself, is the force repulsive or is it a force of attraction? The other two formulae are those that we can use to calculate the magnitude of the electric field. I've labeled them formula number 1 and formula number 2. Very important is that these formulae also only allow you to calculate the magnitude of the electric field. If you would like to determine the direction, we ask ourselves in which direction will a positive test charge move when it is placed in that electric field. Another name for electric field, or when we calculate the magnitude of an electric field, is electric field strength, but we use these words interchangeably. So now the question says, a charge of positive 2 microcoulomb is placed 1 meter to the left of a charge of positive 50 microcoulomb. As you can see, I've drawn a picture to assist us. Very important is that we need to convert these values to the correct SI units. So positive 2 microcoulomb means the same as positive 2 times 10 to the power of negative 6. And positive 50 microcoulomb means the same as positive 50 times 10 to the negative 6 coulomb. Coulomb is the correct SI unit for charge, and we make sure that we do these conversions so that we don't make any mistakes later on. Now question number 1 says, calculate the electrostatic force between the charges. To calculate the electrostatic force, we're going to be making use of Coulomb's law, which says the electrostatic force is equal to K, Q1, Q2, all of this divided by the square of the distance between the two charges. K is a constant of magnitude 9 times 10 to the power of 9, so we plug that in. We have the correct values of the charges. Remember that you always only plug in the magnitude of the charges into this formula. All of this we're going to divide by the distance between the charges, which is 1, and we always remember that we must square that distance. When we plug this into our calculators, we end up with an answer of 0.9 newtons. Now the question was not specific. It did not ask what is the electrostatic force on the positive 2 microcoulomb charge or on the positive 50 microcoulomb charge. So therefore, just to expand on our answer, we're going to say that between these two charges, since they are both positive, we're going to have a force of repulsion. Since we cannot say it's to the left or to the right, it's determined, or the direction is affected by which charge we're focusing on, but here we're looking at the overall charge between the two charges. We know that the positive 50 microcoulomb charge is going to be pushed to the right by the positive 2 microcoulomb charge, and that the positive 2 microcoulomb charge will be pushed to the left by the positive 50 microcoulomb charge. These forces are equal but opposite in direction according to Newton's third law. Let's go on to question number 2. This question reads, we must calculate the magnitude and direction of the electrical field 1 meter to the left of the positive 50 microcoulomb charge. The focus here is the positive 50 microcoulomb charge. We are interested in its electric field 1 meter to the left of it. Now, since we have so much information, we can use either equation 1 or equation 2 to perform the calculation. I'm going to start off by using equation 1, and then I'm going to show you how you can also use equation 2. But in your tests, exams, or your homework, you choose which one of the two to use. You don't need to use both of them. So, the first equation is given as E is equal to F divided by Q. What is important to remember about this formula is that Q is not the charge of the actual charge whose electric field we're trying to measure. This field does not belong to this charge. Instead, the charge that we are subbing into this formula is the test charge. the test charge that will experience a force when it is placed inside of the electric field of the positive 50 microcoulomb charge. Now, since in the previous question we already had another charge placed in this electric field of the positive 50 microcoulomb charge, I'm simply going to use that charge as our test charge. We're going to take the positive 2 microcoulomb charge, and we're going to put it at a distance 1 meter to the left of the positive 50 microcoulomb charge. This here is acting as the test charge. We know its charge, which we of course are going to substitute into the formula in the correct SI unit. But the next question is, do we know the force that this charge will experience as a result of the positive 50 microcoulomb charge? Well, in the previous question, question number 1, we calculated the electrostatic force that each charge experiences as a result of the other. So we know that the positive 2 microcoulomb charge is going to experience a force of 0.9 newtons. Its charge is equal to positive 2 times 10 to the negative 6. And in the end, we end up with the final value of 4.5 times 10 to the power of 5 newtons per coulomb as the magnitude of the electric field. This is the electric field of the positive 50 microcoulomb charge, which this other charge is going to experience, since it experiences a force when it's placed in that field. Now, we only have the magnitude of the electric field. We still need to determine the direction. Remember, we define direction of electric field as the direction in which a positive test charge will move when it is placed inside of that field. This positive test charge is going to experience a force of repulsion as a result of the positive 50 microcoulomb charge. Positive repels positive. So the positive test charge is going to be pushed to the left in this electric field. And therefore, the direction of the electric field is going to be towards the left. Now let's try to use equation 2 to do exactly the same, or to achieve exactly the same thing. We have E equals KQ divided by R squared. Now in this formula, the charge is the charge, or the magnitude of the charge, whose electric field we are trying to calculate. So the electric field belongs to this charge. That means in this formula, our K is still 9 times 10 to the power of 9. But the Q is now going to be the charge, the 50 microcoulomb charge, which we sub in as 50 times 10 to the negative 6. The distance away from the positive 50 microcoulomb charge, where we would like to determine the magnitude of the electric field, is over here, at a distance 1 meter away. So the distance that we sub into this equation is 1, and as normal, we remember to square it. In the end, the answer that we get is 4.5 times 10 to the power of 5 newtons per coulomb. And since when we put a positive test charge here, it is still pushed towards the left by the positive 50 microcoulomb charge, we have that the direction is of course still towards the left. These are the two methods that you can use to calculate the electric field. The most important thing is to remember that in the one equation, Q is the test charge, but in the other, Q is the actual charge whose electric field we are interested in. Let's move on to question number 3. This question says calculate the magnitude and direction of the electric field 1 meter to the right of the positive 2 microcoulomb charge. In this question, we are interested in the electric field of the positive 2 microcoulomb charge. That is the focus of this question. It's that charge that has an electric field around it. So we're going to work this out in the same way, or in a similar way to question number 2. First, I'm going to show you how we can use equation number 1. E is equal to F, so the force, divided by Q, which is the charge of the test charge. In this case, we can use the 50 the 50 microcoulomb charge as the test charge. We are placing it a distance 1 meter to the right of the positive 2 microcoulomb charge. So here we have positive 50 microcoulombs. We ask ourselves, what force does this charge experience? We worked out the force in question number 1 and we found that the force is equal to 0.9 newtons. So into this formula we plug in 0.9 and we are going to divide it by the charge of the test charge. So that is 50 times 10 to the power of negative 6. We always use the correct SI unit. And in the end, the answer is 1,8 times 10 to the power of 4 newtons per coulomb. And that is the magnitude of the electric field. Whose electric field? The electric field of the positive 2 microcoulomb charge. Very important is we also need to determine the direction. So at a distance 1 meter to the right of this positive 2 microcoulomb charge, we put a positive test charge. We ask ourselves, in which direction will this positive test charge move as a result of the positive 2 microcoulomb charge? And since positive repels positive, it's going to be pushed to the right. So the direction here is going to be towards the right. Now I'm going to show you how we can use the second equation, E equals K, Q divided by R squared. In this formula, K is equal to 9 times 10 to the power of 9. It is a constant. The Q that we substitute in is the charge of the charge whose electric field we are trying to measure. So here it's going to be 2 times 10 to the negative 6. We divide all of this by the distance away from the charge. So over here, 1 meter away, where we are trying to determine the magnitude of the electric field. So we plug in 1 and we remember we must square that. We put all of this into our calculators and we obtain an answer of 1,8 times 10 to the power of 4 newtons per coulomb. And since if we put a positive test charge here, it's going to be pushed to the right by this positive 2 microcoulomb charge, we know that the direction is still going to be towards the right. And this is the answer to question number 3. Most important is to remember that Q in these formulae are different, and also to remember that to determine the direction of the electric field, we always ask ourselves, in which direction will a positive test charge move?